Again, you guys know that I've got all kinds of different options when it comes to studying in this class. I've got the notes that are on Google Classroom, and I've got the videos that go together with each of the lessons. And by all means, take advantage of that, right? If you can't remember how to draw a Lewis diagram for an ionic compound, have a quick look at the video and find the way I do that so you can visually remind yourself. Notes are always a good thing to have, though. All right? But what I want to do here again is just go over a very simple, straightforward kind of review for this particular thing. So this is Unit 1, Test 2. All right, review. And really, this is all about compounds. The first one was all about was more about atoms, but this one was about compounds. The first thing we did was formation of ions, all right? And that's when we looked at our periodic table and we looked to see if some elements needed to lose their electrons or to gain their electrons. We started probably with metals, all right? And if I had a metal, for example, like magnesium, Mg, how many dots in magnesium? Am I just going to go this quickly? Yep. 2. It's in group 2, 2 dots. That magnesium is going to lose its 2 dots. We put square brackets around it, and what charge does that magnesium become, Cade? It becomes +2 because it's given away its 2. And when we started to do formulas, we could then use our periodic table. On my table, it's that little 2 right there. On your table, it's that other little 2. But that gives us a charge of +2. And that's the only example I'm going to do here in this little review. But potassium would lose 1. It would become +1. Aluminum would lose 3. It would become +3. Does that sound familiar to everyone? All right? So remember, the number of electrons in that outer orbit, or the number of electrons on a Lewis diagram, is determined by what group it's in. Excellent. We then would have did nonmetals. Nonmetals. And the nonmetals tend to gain. So I'm going to pick one. I'll just pick nitrogen right here. And how many dots around that nitrogen? Tyson, how many dots around nitrogen? 5 is correct. 1, 2, 3, 4, 5. That guy is going to gain, how many is he going to gain? 3. Going to gain 3. That's going to then give the nitrogen a full outer shell. And because it gained 3 negative electrons, its charge is -3. And that's how our nonmetals get their charges, by gaining electrons. Oxygen and sulfur and all those guys in group 16 would gain 2 and become -2. Fluorine, chlorine, bromine would gain 1 and become -1. All right? So our metals become positive and our nonmetals become negative. After we did that, number 2, we did formation of compounds. Formation of, and actually ionic compounds. And I'm going to need a little more board space. Extend the page. So after that, we did formation of ionic compounds. In order to be an ionic compound, what types of elements must there be in this compound? Yep. Metal and nonmetal. Very good. Metal and non-metal. We need a guy on the left and a guy on the right. We then did some Lewis diagrams for those. I'm going to just pick a couple of elements. Let's do calcium with its 2 dots coming together with bromine and its 7 dots. And what am I going to need in order to take care of all of calcium's electrons? Yep. I'm going to need another bromine. That's going to result in a transfer of electrons. That's going to give us, oops, I didn't want red. Oh, let's go to black. That's going to give us, that's not black. What is happening here? That's going to give us a calcium, which is lost 2 plus 2, just like up above. And it's going to give us a couple of bromines. You know what? If you did a big 2, and then you did a bromine, 1, 2, 3, 4, 5, 6, 7, 8, because now it's gained, that would be okay. That'd be okay. Its formula, 1Ca and 2Br. And when we did naming, remember that came from crossing over that charge. That's how we do the shortcut. What was the name of this type of thing? What is this ionic compound going to be named? Yep. Calcium bromide, correct. Calcium bromide. I'm not going to do another example of that. You can go back and look at the video for more examples. We also had a worksheet. Again, it's all on Google Classroom. You can take a look at it. So those were the ionic compounds that we did. After we did that, we did names and formulas. What number am I on? 3? Yeah. 3. Names and formula ionic. Okay. I'm just going to do a couple of examples here. I'll just put here EG, and I'm going to pick something like magnesium nitride. Magnesium nitride. This is where we did that crossover of the charges to get the formula for ionic compounds. Some of you were getting really good that you didn't need to write those compounds down, or sorry, those charges down, but I'm going to write them this time. What's the charge on a magnesium ion? I know we don't have our periodic table, so it might be tricky, but if you can tell me, that'd be great. Yep, Jake. It's 2, it's plus 2. What's the charge on our nitride ion, Cade? -3. It's going to gain those 3. -3. And then we're going to cross those over, and we're not going to write in the charge anymore because they're just telling us how many atoms there are, Mg3 and 2. Okay? If we've got a common factor like 2 and 2 or 3 and 3, we can divide out the 3's and make them become 1's. Remember, when we have a 1, we don't write the 1. We just leave it. We just leave a space there. Okay. And going the other way, I guess if I had something like BeO, we'll just go with BeO. What would the name of that thing be? Yep. Beryllium oxide. Okay. Beryllium oxide. Beryllium. How many L's in beryllium? I get it wrong every time. Is it a 1 or a 2? 2. Beryllium oxide. By the way, folks, for this stuff, if I had something like, and I'm going to do one more, Li2S. For ionic compounds, we don't use mono, di, tri. That's only if they're all nonmetals. That's only if they're all on the right side. So we don't call this dilithium. We call it just lithium sulfide. So we don't use those prefixes. Lithium sulfide. Oops, there we go, sulfide. After that, we did with polyatomic ions. That was that big chart that we had on our periodic table. All right, so you'll be using that. And I know some of the numbers are a little small. I might write it on the board tomorrow if we can't see the numbers. And again, we did a similar type thing with the polyatomic ions. So if I had something like this, K2, CO3. What was that CO3 called? This is obviously potassium. Potassium, and you don't have to have it memorized. You'll have the chart when we do this, but I'm just wondering if anybody remembers what we called it when it had the O's on the end of it. Zach, do you remember? He's checking. No, it's not carboxide. That you're probably thinking of the hydroxide, but it's not that one. Yep. No, it's not carbon dioxide. Nope. 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 This is an ion now. This is a charged thing. This was called carbonate. This was called carbonate. All right? Carbonate. I'm going to address the fact that you want to call it carbon dioxide. Let me talk about that in a moment. That's a good question, actually. Yep. You have the chart. You will have the chart. You will have this periodic table on the test. So you'll be able to see the chart. Yeah, you don't have to memorize that stuff. Let me just go back the other way, do one example, and then I want to talk about why that's called a carbonate, and it's not carbon trioxide, okay? Because there is a reason, and I'll tell you why. So what if I wanted the formula of aluminum phosphate? I would treat that like any other formula. Aluminum, Al. What's the charge on an aluminum? That I think you guys can figure out without the chart. What's the charge on an aluminum? +3. And a phosphate, and I have that memorized, is a PO4, and its charge is -3. Okay? We're going to cross those threes over. What will the threes do? If I've got 3 and 3 crossing over, what do the threes do if I've got 2 of those 3s? Yeah, no. They'll cancel. So that would just be Al and then PO4. They would cancel out. All right? Again, you would have that chart to see what the phosphate is. You don't treat the polyatomic ions any differently than you treat a regular atom. The only difference is you put it in brackets and you put the number outside of the brackets that crosses over. So you don't treat it any differently. Treat it like you would any regular one. Now, why is, and this is a good question, why is CO3 not carbon trioxide? And the reason is it has a charge. Okay? The molecules that we named the other day don't have a charge. So if I've got something like carbon dioxide, then I have CO2, and it's not charged, which means they're not ions, right? Remember, ions are charged. So when you have a group of atoms that has a charge, you don't use that di and that tri. It simply has its own name, carbonate. So this thing is a carbonate. This is a carbonate. And this is a carbon dioxide, like we learned yesterday, di. And the reason for that has everything to do with the charge. If it's a charged thing, we don't use those rules anymore. It has its own name. Okay? When you're looking at it up here, you'll notice you can't see the charge, and that's because it's been canceled out by the potassium's opposite charge. So when it's in an ionic compound, it will always be the ionic name, carbonate or phosphate. When it's all by itself, then you use the mono, di, tri, etc., etc. Yep.
So if you had a CO4, would you call that carbon tetroxide?
Tetroxide, correct. It doesn't exist. There is no carbon tetraoxide. Because of the way the carbon's electrons line up, they wouldn't line up with 4 oxygen atoms nicely. But if it did, that's what you'd call it. Yep, that's correct. Okay. All right. So after we did that, we did some molecules. So I think I'm on number. Anybody keeping track? 5. Number 5. Number 5? Oh yeah, because I did polyatomic separate. Number 5. Number 5. Molecular substances. And that's where we have two nonmetals, non-metal and a non-metal, and they don't have a charge. If they had a charge, they'd be an ion, just like I talked about a moment ago. We did some pictures. Let's do carbon dioxide as an example. Carbon, 4 dots, 2 oxygens. How many dots in an oxygen? 6 dots. 1, 2, 3, 4, 5, 6. I'm going to put the other one on the other side because I know this way this is going to look. 5, 6. I make my connections to make my bonds. Uh-oh, that was bad. This guy's got to go all the way over here. That's ugly. But you get the idea. And in the end, I can turn those red lines into the proper bonds. I have to put my lone pairs also on the O's. And that's a good old carbon dioxide. Doesn't have a charge, so we call it carbon dioxide. Okay? So that's how we draw them. And we had some example problems. I'm not going to do a million of them. This is just a quick review so that you can get to work. Oh, and I got to click on extend the screen. And then yesterday, we learned how to name molecular substances. And that's where we use the mono, di, tri, et cetera, and that's actually the way I'm going to describe it. Mono, di, tri, etc. You get the idea, I think. It's supposed to be a review, so it's supposed to be a shortened way of thinking of it. So an example, there's so many different molecules, it's not as easy to make them up. Let's go with Cl2O. We'll come up with a name for that. And then we'll come up with a formula for dinitrogen monoxide. Name for the first one. What do you think, Tyson? How many chlorines? So what do we need on the front? Dichlorine. But I've got 1, so I need something monoxide. The only time you don't use mono, if it's 1 on the front end. Dinitrogen monoxide. What is the formula going to be? What's the formula going to be? Yep, what do you got? Huh? N2O1, and we don't write the 1. All right? Okay? The final thing I did, and actually I did it yesterday at the beginning of class. Let me just move that down a little bit. I know some people are writing. And I know I'm kind of rushing a little bit, but it is supposed to be a quick little review so that it's kind of all in your brain, so when you sit down and do that, you're in good shape. And what we did there was properties. And it was just a summary of the properties: ionic, molecular. Over here I would have had conductivity as solid. So con means conductivity. Are we okay with that little thing there? And as a solid, we put those conductivity meters as a solid. What am I putting down for those things? Remember doing the experiments? For the solid, what did the light do? Okay, it did nothing. No and no. No and no. Conductivity as a solution. In other words, dissolved in water. Conductivity as a solution. Yep. Yes and no. Yes and no. And the last thing we were looking at was melting point. Click. That's going to be my end. And I'm going to just put here good old MP. We always just put MP for melting point. So melting point for ionic. Logan, that stretch looked like a hand up. I'm taking it. What's that? Hi. Hi. And you might as well finish it off, Logan, since you're so energetic there, yawning. What's that? Low. Low is correct. Okay, so that's all I wanted to do was just a quick little kind of gathering up of all the things that we did. So at this point, if you think that that's good enough to tweak your mind into working on the review sheet, that's great. You can go ahead and do that. The review sheet, obviously, on Google Classroom, you could get a stylus and you could write on the review sheet there, or you could write it on a piece of paper, however you want to do it. And I have the solutions in a PDF right underneath it. So if you don't get it done in class, you can check it tonight and have a look over to see if you're getting them right. Okay, I'm going to stop the video, and then you guys can work away. Okay.